Welcome to Steady Heat Conduction. Start with the simplicity of steady heat conduction. Before we get into complex cases, let's start with the simplest heat transfer scenario, steady-state heat conduction. This happens when temperature doesn't change over time, making the math easier and the results clearer. Think of it like the calm before the storm. Steady state helps you understand the fundamentals of how heat flows through materials without the complication of time dependency. Mastering steady heat conduction builds your foundation before you explore transient or multidimensional cases. Make sure you're solid here. Focus on practical and useful learning outcomes. Let's be clear about what you'll gain. A strong learning outcome focuses on practical skills you can apply, not vague promises. Here, you'll learn to use thermal resistance like an engineer, solve problems using resistance networks, and tackle real-world shapes like walls, cylinders, and spheres. You'll also handle special cases like contact resistance, know when insulation increases heat transfer, and work with finned surfaces. Finally, you'll master shape factors to simplify complex geometries. Every outcome is action-oriented, built to make you a more effective engineer. 2. Make thermal resistance intuitive. Great teaching connects to what you already know. Thermal resistance works just like electrical resistance. Think of temperature difference like voltage, heat flow like current, and thermal resistance like electrical resistance. With simple formulas like R equals L over Ka for conduction and R equals 1 over Ha for convection, you can turn complicated systems into easy-to-handle resistance networks. Add them up like simple circuits, and you can predict overall heat transfer quickly. Focus on resistance thinking. It simplifies everything. 3. Keep plane wall conduction simple. Let's cut through the noise. Steady-state conduction means no temperature changes over time. It's predictable, simple, and fast to calculate. With the basic formula, Q equals Ka times T1 minus T2 over L, you can easily compute heat flow through plane walls. When walls have multiple layers, it's just like resistors in series. Add up the thermal resistances. Focus on this simplicity. Understand the basic flow first, then you can handle more complex setups with confidence. 4. Make complex shapes simple. Not all systems are flat walls, and that's okay. For cylinders and spheres, we just adjust how we calculate thermal resistance. Use the logarithmic formula for cylinders and a simpler fraction for spheres. Both follow the same logic. Temperature difference drives heat flow, and geometry modifies resistance. Don't let the shape confuse you. Apply the right formula, get the resistance, and solve the problem just like you would with flat walls. Simple and consistent. 5. Don't ignore contact resistance. Heat doesn't always flow smoothly, especially across interfaces. Thermal contact resistance happens because surfaces are never perfectly smooth. It depends on surface roughness, material type, and contact pressure. The good news? You can reduce it. Use thermal grease, metal foils, or even swap air for helium to lower resistance. When you troubleshoot heat flow problems, always check the contact points. Sometimes Fixing the interface fixes everything. Don't be fooled by insulation. More insulation isn't always better. In some cases, adding insulation actually increases heat transfer, especially in cylinders and spheres. This is where critical radius comes in. If your insulation is below the critical radius, heat loss increases instead of decreasing. For cylinders, it's K over H, and for spheres, it's 2K over H. So before you add insulation, check the critical radius. It helps you avoid making the problem worse. 7. Use fins to boost heat transfer. Sometimes you don't need to change materials. You just need to add surface area. That's where fins come in. Fins increase heat transfer without increasing temperature difference. Focus on fin efficiency to see how well your fins perform. Choose the right type, rectangular, triangular, or cylindrical, based on your design goals. Simple equations help you quickly estimate heat transfer from fins, especially for long or adiabatic tip fins. Don't forget overall fin effectiveness. It tells you if adding fins is worth it. 8. Simplify complex shapes with shape factors. This is where conduction shape factors S make life easier. Instead of complicated calculations, you just multiply by S to quickly estimate heat flow. Think buried pipes and parallel pipes in concrete. You don't need advanced math, just grab the right shape factor from charts or tables. Focus on this shortcut. It saves time and delivers solid engineering estimates, especially for tricky real-world configurations. 9. Connect engineering with biology using bioheat equation. Heat transfer doesn't stop at machines. It happens in biological tissues, too. Here, you need to account for conduction, blood flow or perfusion, and metabolic heat generation. Penny's bioheat equation combines these effects into one formula, helping you analyze heat flow in the human body. It's especially useful in medical treatments like hyperthermia therapy or burn analysis. Remember, same heat transfer principles, just applied to living systems. It's a great example of how engineering concepts cross into medicine. 10. Turn theory into practical engineering applications. Every concept you've learned shows up in real-world designs. Thermal management in electronics uses heat sinks to cut down resistance. Heat exchangers get better with thinned surfaces for faster cooling. In insulation design, it's all about balancing cost and performance, optimizing not just for heat reduction, but for economics too. Always connect your learning to real-world engineering problems. This is where theory makes you a better problem solver. Let's close by sharpening your focus. This session equipped you with steady-state conduction tools for walls, cylinders, and spheres. You learned how to simplify calculations using thermal resistance networks, and when insulation can increase rather than decrease heat loss. You explored fins for better heat transfer, shape factors for complex geometries, and bioheat transfer for biological systems. Keep your focus sharp. These are tools to simplify, optimize, and apply theory to real problems. Use them wisely.